because that's really what we're concerned about. And you can see here, this is a photograph of our sample after exposure to this wear test. Here's the wear scar. Here are the results. In the orange column, you have the volume loss. White columns are your micro hardness. Now, yes, our hardness increases by about 50%. That would lead to decrease in volume loss. But this is not what anyone expects. Even with this increase in hardness, you would not expect such a dramatic decrease in volume loss. But it's because of the fact that you're increasing toughness in addition to the hardness or strength that gives you a huge drop in volume loss. And this is great. This is something that we did at McGill years after we carried out all those tests. We decided to look at the wear scars under the microscope. And this really validates the fact that we had a tougher coating. Because this is typical of brittle fracture. You have a lot rougher surface. Here you see that we have a smoother surface, which is typical of ductile materials such as metals and plastics. And that's because you have a lot of plastic deformation, microcutting, microplowing. What we're noticing here is that majority of fracture occurs between at the splat boundaries, which means one droplet solidifies, the next one comes. The boundary between the two is the weak spot. So it forms a crack there, and that chunk falls off, leaves you a fairly rough surface. We also carried out some slurry erosion tests. This was carried out at the National Research Council of Canada. And basically, you pump your slurry through a nozzle, you accelerate that onto your coated sample. You can change the orientation of your samples so that you can get different impingement angles. And that's really important. And the reason why is shown here. You have erosive wear versus impingement angle. And you can see, depending on the type of material, you get very different types of wear. For ductile materials, they wear a lot at relatively low angles, around 30 degrees. And then it decreases dramatically at high angle. Whereas it's the opposite for brittle materials. So it's important, if you want to really know and understand how your material is going to perform against erosion, that you do it at different impingement angles. And here are the results. In the orange columns, these are wear or volume loss at low impingement angles at 30 degrees, and then here's the 90-degree high impingement angle volume loss. And this, once again, is unique. No one has seen that before, where you have a decrease in both low and high impingement angles. Typically, if it decreases for material, it will increase at the opposite impingement angle. However, because, once again, you've got something harder and stronger and something even tougher, you can have direct improvement in both impingement angles. And that's really good. So here's the wear scars on after low impingement angle slurry test. You can see here, there's very little directional scarring. Directional meaning, you see here, there's a lot of scars that run along that plane, primarily because the erodent was projected along that direction. Here you see there's one here, however, majority of it is non-directional. Brittle fracture, cracks and faults. So this, once again, really shows that this coating is behaving ductile, more ductile, when in fact it's harder. And even at high angle impingement, you have higher roughness, but compared to the commercial coating, you see that it is smoother. The craters, the edges of the craters are rounded. And that's, once again, this is what you typically see with metals and polymers. So as John Williams likes to say, the proof of the pudding is in the eating. I never heard that before, John. But it's great. We do all this lab scale tests. It looks great. But how's it going to fare in service and field application? It's really difficult to get the mines to track a component very closely, especially with different coatings. However, in this case, here at Gold in Papua New Guinea, they they took the initiative to evaluate two types of coating. This is a coating blend, chromium oxide, which they were using prior to our introducing nano-TiO2. They want to see a direct comparison, so I understand, they took two 10-inch Ti64 valves, applied the coating, they're identical valves, they applied two coatings on it, and then put it in service parallel. So they're exposed to the same conditions, same duration of time. So after 10 months, they had leakage in this valve, so they removed both to look at it. You can see there's gross spallation of the coating on the chromium sample, whereas with the nano-TiO2, these red regions are scale built up. But the coating remained intact, and I believe they put it back into service for more use. Now, someone at Murrin, as a mine in Western Australia, thought, okay, well, if it's doing well in that application, how well will it do in erosion, pure erosion application? So these are impeller blades or stirring blades. This is their lab scale setup. Nano-TiO2 coatings were applied onto these blades, and they carried out their standard test. And the response from them was that the nano-TiO2 resulted in over 2 times better wear resistance, erosion wear resistance, compared to what they were using before. And apparently there are 46 field blades that have been coated with nano-TiO2. That was carried out a year and a half ago. And the fact that, I like to think that we haven't had any use is good news. Usually they're not shy about, letting me know when something has failed. So here are several locations around the world where nanostructured TiO2 coated valves are being used. And from my understanding, John has mentioned that we estimate around 1,000 valves that have been coated with nano-TiO2. So that was pretty good success. I'm going to move on to a potentially attractive application, specifically on N-Crollies, and in this case we worked on nickel chromium alumination. Specific for bond coats in thermal barrier coatings, and we were using non-cryogenically milled powder, primarily because a lot of the work on nanostructured metal revolved around cryogenic milling. And that's great, and it's great for space application. Rocketdyne is using it, but it's expensive. And for military as well as many other applications, the cost of the powder, if you're cryogenic milling, is too high. So we're working with non-cryogenic milling, and we're working on this with Angela Moran at the Naval Academy, as well as Tony Adana at Edwards. So the objective is to develop an economically viable nanostructured bond coat with superior protective performance properties. It revolves around this the gas turbine engine. And you have the compressor section, the combustor section, and the turbine section. And we're focusing here on the combustor section, the hot section. Obviously, high temperatures really cause havoc to these materials. We're talking about hot gases in excess of 1,000 degrees Celsius. Not a lot of materials can withstand that for extended periods of time. Now, gas turbine engines are used for jets. They're used for land-based reduced energy, electric energy, and they're used on ships, on electric boats. Now, there's a strong push to increase the turbine inlet temperature. And you can see why. When you look at the thermal efficiency of these engines, they increase dramatically the more you can ramp up this temperature. The only issue, once again, is as a material scientist, how can you produce materials that can withstand higher temperatures for long periods of time? And that's a real problem. And in addition to higher thermal efficiency, when you can increase the temperature, you also decrease the pollutants from these engines, which is obviously an important factor also.